All right, let's go a little further in simple harmonic motion, and now let's talk about a physical pendulum and a torsion pendulum, and I'll show you that they're exactly the same thing. A physical pendulum is just a board. I'm going to put a dot here because that's where the center of mass is, and so that'll be important when we look at the torque. So we'll start out with torque equals I alpha, just like we did for the simple pendulum. The torque is going to be negative mg, right? There's the force. Right, mg is down, except the lever arm here is going to be L over 2 sine theta. The moment of inertia of a board pivot on the end is 1/3 ml squared, and alpha can be written as theta double prime. Let's get rid of those m's. Let's get rid of one of those l's. Sine theta is approximately equal to theta for small angles. Again, it's the small angle approximation. And then what we're left with is negative that 3 in g, 3g over 2l theta equals theta double prime. And again, I'm going to put a box around it. Again, this is a second order differential equation. I'm not expecting you to solve it, but I am expecting you to know the pattern. Once you've established this differential equation, it's just like knowing y equals mx plus b. If I wrote down y equals 5x plus 4, you don't have to solve this. You know right away that 5 is the slope and 4 is the y-intercept. It's the same thing because you understand the model y equals mx plus b. Well, now I'm asking you to understand the model negative omega squared times a function equals the second derivative of that function. This number, you just look at it and you know that it's omega squared. But if you know it's omega squared, then you can write theta as a function of time. It's some theta naught or max times cosine of omega t, where omega is the square root of 3g e over 2l. But then we also know how trig functions operate, and the period is going to be 2 pi divided by omega, which is 2l over 3g. And it's very similar, the physical pendulum period, to the normal one, except it's got that 2/3 factor. It's going to oscillate a little slower, meaning a smaller period. The torsion pendulum, I know my picture's not great, but this is just some fixed structure, and we're going to hang a wire from it, and the wire is going to be attached to the disc. And what you're going to do is you're going to take the disc and you're going to twist it. And if you release it, it's going to go whoom, 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 whoom. It's going to rotate and then unrotate, and rotate and unrotate. It's similar to like putting a kid on a swing. Hopefully at some point in your life you got on a swing, you twisted the rope, and then you let go, and the kid spun, and then probably then respun even the other way. And it would be this simple harmonic oscillator where it spin one way, continue to spin past equilibrium, and basically spin up, and then spin the other direction. And so what we were going to say is this would be a given. It'd be given that the torque is somehow proportional to the angle. This piece is given to you by the problem. It says that the restoring torque of the disc is opposite, somehow proportional to, depending on what type of wire it is, to the angle, meaning the bigger the angle you rotate through, the bigger the torque. And so now we go to our basic torque equals I alpha. The torque we know that this torsion pendulum is applying is k theta. That equals I theta double prime, and we divide and we're done. Because again, we put it in the form that we know. Once it's in this form, we know that this has to be omega. Oops, that has to be omega squared. So omega has to be some k over I. And maybe you know the I. Maybe it's a disk and it's 1/2 mr squared. But even if you don't know the I, you can just write it like this. And then we know this. Then we know the period for this motion is going to be 2 pi divided by m over k, I over k. And that's our torsion pendulum. Both of these things operate exactly the same. They both get the same differential equation. With the differential equation, you can read off the period, you can read off the omega, you can get the equation of motion. Again, the equation of motion here will be some original theta you displaced it with times cosine of omega t, where you know cosine. Okay, so that's the physical pendulum and the torsion pendulum. You should know all four of them. So this guy, and then our classic mass on a spring, and then what they would call a simple pendulum was just a ball on the end of the string.